All right, so we're going to continue section 12.4, and I'm going to start by just giving you all a couple of important parameterizations that you're going to want to remember basically throughout the remainder of the course. So first, and I'll put asterisks next to these. A parameterization for a line segment from, and it's important that we have where we're starting and where we're ending, a point P naught with coordinates x naught, y naught, and z naught to a point P1 with coordinates x1, y1, and z1 is the vector function r of t equals the quantity 1 minus t times the vector r naught. And that is just going to be the vector that corresponds to p naught, but I'll specify that in just a second, plus t times the vector r1, where, so it's very important that you specify what t varies between, otherwise you'll get, you want to make sure that you just get a line segment versus getting a full line. So here t has to vary between 0 and 1. So t varies between 0 and 1. R naught is just the vector with components x naught, y naught, and z naught. And R1 is the vector with components x1, y1, and z1. So if you want to, of course, you can just put that right there and put this right there if you want to rewrite the formula that way. All right, so next is we let y be equal to f of x. So now we're just working in 2 dimensions here. So this is what we were accustomed to and seeing in courses before, Calculus 3. Be a continuous function. We can parameterize the curve C, traced out by y equals f of x, by letting x equal t and y equal f of t. Then a vector function for the curve C is just the vector r of t. Its first component is just as usual, or whatever our x is, which is t. And the second component is whatever our y is, which is f of t. Now, remember that we're in 2 dimensions here because we have a function of 1 variable. If we were in 3 dimensions, we have a function of 2 variables. And we don't have, we haven't talked about, or we're not talking about here doing a function of 2 variables. We're just doing a function of 1 variable. We have done some parameterizations in 3 dimensions, but this right here only works for 2 dimensions. And we'll talk about some more parameterizations for stuff in 3 dimensions. All right, so now let's look at some examples from your textbook. So we're on page 786. These 2 parameterizations, I pointed these out in particular just because they're going to be important throughout the course. And in this section, you'll see some problems that ask you to parameterize line segments or curves in 2 dimensions that are just given by a continuous function y equals f of x. Those are the parameterizations you're going to use for problems of that sort. All right, so we're on page 786. And we're going to start with number 12, which says in exercises 11 through 20, find a smooth parameterization of the curve described. So the straight line from 0, 3, negative 2 to 6, 1/2, negative 2. They say a straight line. I presume they mean the line segment when they say from and to. So line, and I'm going to do line segment. Line segment, although they don't say it in the textbook. From 0, 3, negative 2 to 6, 1/2, negative 2. And let's call this, I should have called this P0 and P1. So let me see if I can squeeze that in there. That's P0 and that's P1. All right, so now we're going to use one of those parameterizations I just gave you all. There's RT equals 1 minus T times R0, and our R0 just has the same components as P0, so you can just write the vector right there. 0, 3, negative 2, and then plus T times the vector with components, the same components as P1, so 6, 1/2, negative 2. Now, with the exception of making sure you write that, of course, you can leave this part exactly like that, but make sure you do include where T varies from so that you know you're starting at that point and going to that point, and that's it. And if you look at this, you can see as T equals 0, this is gone entirely, and this is just 1. So all you have is that point, and at T equals 1, this is 0, so this is gone entirely, and you have a 1 right here, and you have that. So you're going to vary from this point or this point to that point right there. All right, next let's look at number 14, which has the same directions. So we're finding a parameterization. So the circle in the XY plane centered at the origin with radius 6. Oh, sorry, that's the wrong question. I read 13. The circle in the plane z equals -1 centered at 2, 4, -1 with radius 5/2. Okay, so sorry. So what we're going to start with in a problem like this is we start with what we know. So the same thing we did in the last section is that we were given parameterizations in the last section, and we tried to figure out what those curves look like. So we're familiar with working with x, y, and z. So although we were given a vector function in the last section, we would take that vector function and we would try to eliminate the t's if at all possible. So we could just work in terms of x, y, and z because that's what we're familiar with. Here, they give us a verbal description of, or a written description of the figure. We're still going to start with x, y, and z because we're more familiar with that, and then we'll translate from that into a parameterization. So now we're going to, instead of eliminating the t, we're going to be getting the t, or coming up with the vector function that has the t in there, or the parameterization ourselves. So let's just start with the circle centered at 2, 4, -1 with the radius 5/2. So, and we're stuck in the plane z = -1. So our z value is not going to vary at all. So x minus 2 quantity squared plus y minus 4 quantity squared. And we're not going to have a z on here because we're not talking about a sphere, we're talking about a circle, equals our radius squared. And remember, if we don't specify z in this class, this will be a cylinder. All right, but we don't want a cylinder, we want a circle. So we're gonna specify z as they told us, where z is equal to -1. All right, so the z is always -1. The center of this circle, if you were to look at it in the xy plane, or you slid it up to the xy plane, it would just be 2, 4. But because we're at z = -1, our center is 2, 4, -1. It's the circle slid down to the plane z = -1. So this is what they describe for us. Now, they want a parameterization of this. So just think back to when we had a vector function, and we found out that that vector function was a circle. What we ended up using every time is we had sines and cosines in there, and we would use our favorite trig identity. So we're going to do the same thing here. We're going to go backwards. So this is another reason that is our favorite trig identity, because it gives us a means by which to write any number, because it has the number 1 in it. So I'm just going to start by rewriting x minus 2 quantity squared plus y minus 4 quantity squared equals 5/2 squared. And my favorite trig identity allows me to write 5/2 squared in terms of sines and cosines. So this is the same as 5/2 squared times cosine squared t plus sine squared t, right? Because this is just 1. So now I've written 5/2 squared in terms of sines and cosines. So to make it a little more clear, that's equal to, I'm just going to distribute this through here. So 5/2 cosine of t quantity squared plus 5/2 sine of t quantity squared. So now I have that this sum of squares right here is the same as this sum of squares over here. So I'm going to let x minus 2, so put a squiggly line under that, be equal to 5/2 cosine t. And I'm going to let y minus 4, and put a straight line under that, be equal to 5/2 sine of t. All right, so now that'll give me my parameterization that I want. So let x minus 2 be equal to 5 over 2 cosine of t, and y minus 4 be equal to 5 over 2 sine of t. And we already have what z is. Z is 1. So now we just want x, y, and z, so we have our parameterization. So x equals 2 plus 5 halves cosine t. So 2 plus 5 halves cosine t. Y equals 4 plus 5 halves sine t. And z equals negative 1. All right, we don't need to put a restriction on t in this scenario. I mean, it's understood that here t, whatever your t is going to move in the positive direction, and you have to make sure that you t runs far enough for it to trace out your entire circle, because that's what that gave us. But we don't need to put a restriction on t, because if we let t go forever, it's just going to keep tracing the same circle over and over and over again. So, which is perfectly fine, as long as we're not trying to find the length. Now, we'll get to in our next video finding the lengths of such curves, and we need to make sure we only trace it out once. Otherwise, we won't have the length of the curve. We'll have something, the length of something that's longer than the curve that we initially had, or that we initially wanted.